Cool, so thanks for joining me in this introductory journey through Kubernetes networking. We are going to have a lot of fun. Let's start, before the presentations and all that, with a show of hands. How many of you, raise your hand if you interact with Kubernetes more or less regularly? Use your own definition of regularly. Okay, bit over half, that's okay. So what about networks? How many of you interact with networks willingly, not by means of, browsing the internet? Okay, also about half. This will be fun. Let's go. These are my people. Cool. So, before jumping into the meat, this is the mandatory about me presentation. My name is Nadia Santalla. I use she, her pronouns. You can find my website and my email in the slide. I'm a senior software engineer at Grafana Labs. In my free time, I read books and collect machine tools. And when I'm not doing that, I'm touching computers, mostly regarding infrastructure and Kubernetes. Not a lot of code. Cool. What's the agenda for today? We're going to do a very brief introduction, and by brief I mean it's only one slide about containers, pods, and services. We're going to talk about the container network interface, mainly what that is. Then we're going to delve right into the meat with pods, services, cluster DNS, and ingress. So let's start. Containers, pods, and services. So if you more or less have ever heard about Kubernetes, you have probably heard about containers, pods, and services. At least containers and pods, right? So let's state a few facts about this, just to try to be more or less on the same page. Let's start with containers. You are probably familiar with this. You know the thing that you build with Docker build, and it's basically a self-contained, or you can call it a self-contained application image. So you put your application in there, and in the same place you put everything your application needs to run. And that's amazing, because then you can run it everywhere. They run on dedicated namespaces, so both Docker, Podman, Kubernetes, basically the whole point of containers is that they run with certain isolation. It is not very security-oriented isolation, but it is some kind of isolation. And in Linux, call these namespaces. So containers usually run on their own network namespace, process namespace, and some others that I don't know by heart. Something that is important and maybe surprising, especially if you are not that familiar with Kubernetes but you are with Docker, is that in Kubernetes containers do not have an IP per se. So you can have multiple containers in the same pod, and all of them will have the same IP address, because it's the pod who have the IP. The pod, speaking of which, obviously has an IP address, belongs to a node, and can group one or more containers. Usually one is often considered best practice to have one container per pod, but you do not necessarily need to. And the latest bullet there is what I wanted to emphasize. The pod is the smallest compute unit in terms of, as far as Kubernetes is concerned. That means that in Kubernetes, containers are actually second-class citizens. You always manage pods. So pods have addresses, pods are the ones that you communicate, pods are the ones that you scale up and down, that you create more, that you delete. So you do not interface with containers directly. So from here and onwards, we will pretty much forget about containers and we will talk about pods. But it's, in the end, is the more or less the same concept. And another of our protagonists this afternoon is the service. So a service is a bit of a more abstract concept. You will see. I will explain a bit why. But a pod is something that is very tangible, right? It is running on a node. It is there, and that's it. There is to it. Services are a bit more vague, because they do not really exist anywhere. The data for them is obviously in the control plane, but they do not really belong to any node. And they are typically used to reach pods, or to reach groups of pods, and perform load balancing across them. We will see this in more depth later. But yeah, one of the key things is that while the relationship between a pod and a node, for example, is I would say a strong relationship, the pod is running there. Services group pods in an orthogonal way. They select pods, it's like you, and you are going to be part of this service, and the pod don't really have a say in that. It's basically a very loosely connected group of pods. You can see in this diagram is not mine, this one I stole from the Kubernetes documentation, and you can see a bit because the font is really tiny, but you can see the nodes, which are the purple squircles with pods inside, and these heptagons that are outside of the squircles, those are the services, and you can see how they can select pods across nodes without much hassle. Cool. So I've talked about how pods have IPs and services have IPs, and you may be wondering why this? Like, why so many IPs? Is there really a need for this? You know, I have a single machine and I run 100 services on my machine and it works perfectly. Well, yes, and that's perfectly fine. The reason that pods have IPs is rather stems or distills rather naturally from the assumptions and the use cases Kubernetes is thought for, right? For example, one of the Kubernetes premises is that any number of pods for any application can be scaled on any node, right? So let's imagine that we have an application that is using port 80. Can be Nginx, can be a web service, can be whatever. It is using port 80, right? So if I want to create 2 replicas of this application, and I want to put these 2 replicas of the application in the same node, that is kind of a problem, right? If we try to think like how the world was before containers, it's like, okay, these 2 processes want to use port 80 and the node only has 1 port 80. So that's a bit of a problem. However, if we give each of these instances of the application its own IP address, then we do not need to care. We just give the application the address. Yeah, sure, you are on port 80. You are free. So it's one of the this is one of the reasons why this is such, right? It unlocks the possibility of just letting the application do its thing, and we do not need to worry about where it is running or what port it is using. And another thing why this makes it easier is for load balancing. If we can treat an application, well, it will obviously have a pod, but if we can treat different instances of application at different IP addresses, then load balancing is suddenly very easy because we can use whatever tooling it is available. One could argue it will be easier as well if we have multiple, if the applications were sharing addresses, and it is true, but it does simplify things along the way implementation-wise. We will see that a hint of that later. Okay, hopefully I have convinced you that pods having IPs is a good idea, and you may be wondering, okay, but why services? Why services do also need IP addresses? Specifically, if you are network-minded, you might be thinking DNS can already do that for us, right? So we have 3 instances of the application, we could have a DNS A record and return all 3 IP addresses, and the client will do the load balancing, right? This is like we've been doing this for decades now. It should be work. It should be fine. Well, it turns out it is not very much that fine. There are a couple problems with that approach. It works for the most part, but it makes some things a bit complicated. And in the end, it turns out that dedicating one IP address to the service, it's a bit more of, it creates a bit of overhead, but it does eliminate this problem. So in the end, I think it is worth it. What are some of these problems? So, for example, if we do this, if we have this record, this name that resolves to 3 addresses, what happens is these addresses change relatively often, right? So, for example, these addresses will be pods, and we have one pod die and get replaced with another. Then we have a caching problem here. The client who has resolved all these 3 addresses may try to reach one of those, and that is no longer available. So we need to kind of be able to expire that address. So we set a TTL for our record. And in the harsh reality, it turns out that many clients simply ignore TTL records for DNS. Like they are just broken libraries, or they were done in a pinch, and you know, caches and many things are the two hardest problem in computer science, so they didn't even bother. There are other type of applications which are also which are also known to do the lookup when the application starts. Like, okay, this is my IP address. I no longer care about this name. I will forget about this and use this IP address until I die. And you can see how this is a problem if we are rotating the backend software. And so even if we happen to find a client application which is amazingly written and that respects TTLs and that it resolves the name periodically, then if we want for our system to be actually responsive, then the TTL we will need to set for that record will be very low, like 0 perhaps, or maybe a couple seconds, because during that window there is an opportunity for all pods to get replaced, and then our application will be seen offline. So if we actually set that very low TTL and the application respects this, what will happen is that we will create an enormous load in the DNS server. So the application, all clients will be constantly spamming the DNS server. Like, have the pods change, have the pod change, have the pod change, and that will not be particularly great. So those are three, I believe, important reasons why services have IPs and why applications are not bothered with load balancing using DNS records. Hopefully I have convinced you. Let's talk about CNIs before we get into the pods and services and how they work. And CNIs is actually a bit abusing the thing. CNI stands by Container Network Interface. You may have also heard the Container Runtime Interface, the CNI, in the times with the Docker Shield application and Containerd and Cryo and all that. So CNIs are like CNIs but for network. And this is because you will see this is a recurring theme in this presentation, and obviously in Kubernetes in general, but there are many things Kubernetes does not concern itself about, and instead delegates to other pieces of software, so sometimes very optimistically. And network is one of those. Implementations, the software that actually implements the container network interface, the name interface comes because there is a specification, you can look that up. That is basically telling, okay, Kubernetes and actually other software will expect your software to behave like this and to be callable in this way with shit on environment variables and commands. And your software, which is implementing the CNI, will need to do this. So all these implementations, like Helium, like Calico, are actually called CNI plugins. In reality, we just call them CNIs. That's a bit of abusing terminology, but when you see people talking about the CNI or a CNI, they are most likely not talking about the interface, the specification, they are talking about the specific implementation. So what do CNI plugins or CNIs do? Quite a lot of things, and some CNIs do more than others, but the very basic thing is that they should create network interfaces for the pods. So when the pod exists and inside the pod you can run IP address and IP route, we will do that and you will see it. There is actually a network interface in there. That interface needs to be created, registered in the kernel for the host that is running the pod. The CNI will do that. Most of the time, the CNI will also allocate IPs for that pod. So the IP address that pod has, that has been determined by the CNI. Not always, there is a bit of a blurry line, but for the majority of the cases this is true. And most importantly, CNIs will make the network work, right? So we have a pod, we create an interface for it, we give it an address. Now this address should be functional. This address should be able to talk to other addresses. This is one network for. And this is the meat of the work, the biggest chunk of the work of the CNI. Make that possible. We will see a glimpse of how later. Cool. We are done with introduction. Let's talk about pods. So we already more or less know what a pod is. Collection of containers is running somewhere, which has its own IP address, it has its own interface, and it also has routes. IP networks need routes to work. Multiple containers inside the same pod are actually run in the same network namespace. This is different from Docker, again. And what this effectively means is that they share the same local host. So, if you tell a very networking person this sentence, they will yell at you, but between us, we are close friends, we can say that. They share the same local host. And it's the CNI plugins, the ones that make the stuff available. So, what do we have here? This is some dumb example, that I wanted to show more how this, the glimpse of how this works. So, in the bottom left, you see a very tiny snippet of a pod. It doesn't matter what name it is, but you can see there is a pod in there and has the IP address 10.185 for 19. So if we go into that pod and we shell into a pod, that is the top right code snippet, and we type IP address, we will see that particular output is uncropped. That's all that you will see, and you can see that there is a loopback interface, and obviously there is localhost available, and you can see that there is a weird interface in there. It is 0 at yada yada with that IP address. You can see there's a /32 that might be a bit strange, or you most likely see other prefixes more used, but it will make sense in a moment. And if we run into the same IP route, that's the second command in the same snippet, you will see that the output is a bit unusual as well, because you typically see some via link yada yada, because things are normally on a local area network. This one is not, and you can see that it has a default route that it says everything goes via this specific IP address, which is not the address of the pod. And there is a second route that is saying, okay, this default route is reachable through this interface. So what is this address really? So just by the output of the command, we can say that, okay, this address is the gateway for the pod. So every time the pod needs to communicate with basically anything else, anything that is not localhost, it will go through here. And this is a bit implementation dependent. Different CNIs will manage this in different ways. Hopefully, it will be a bit similar. This is for Cilium in particular, which is the one I use. Happen to like it. And the Cilium implementation in particular works like this. There is this special IP address that will be one per node. And if we go to the last code snippet, which is the bottom right, you can see that I'm running IP address on the node, not on the pod. And you can see that there is a kind of special or weird interface called Cilium host as Cilium net, which has this IP address that the pod was told to use as the default route. And what will happen here is that there is the Cilium in particular, the CNI, will figure some way to make this traffic work. For Cilium in particular, it is through eBPF, so there is a tiny agent on each node that is going to register all these flows and where things can and cannot go. How does this work a bit more in practice when pods communicate? Again, this will depend vastly on your CNI. Different CNI implementations will make this possible through different ways, but almost always will be by interfacing with the kernel networking primitives. So the CNI plugins will rely on IP tables, that is the net filter subsystem. They will run IP tables command. They may rely on IPVS. IPVS is a load balancing, layer 3 load balancing component of the kernel, IP set, IP route, and BIF. BIF is virtual Ethernet if my memory serves. So when these two pods that want to communicate are in the same node, this is relatively easy as far as interfacing with the networking subsystem of the Linux kernel goes, because all the state all the logic is kept in the kernel. So as long as you tell the kernel, this is here, this you can communicate, and you make the things possible, then that's okay. We are
Sorry.
yes.
Another question, please. About tunnels, for example, I understand that the tunnel will be another primitive. No? We will put the tunnel there, and we will route everything.
Yes, there will be tunnels on the next slide.
Okay.
Yeah.
I'm very interested.
Yes. Not a lot, but they will be mentioned.
Good.
So again, within the same node, the kernel can keep track of all of this, and the kernel can do its thing, and we are all very happy. Now, pods obviously can communicate with pods that happen to be in other nodes, and that's actually a quite important thing to happen. And again, depending on your CNI and depending on how you configure it and many different things, there are many different ways this can happen. I'm talking here about two, just because I think there are two that are particularly relevant, but they are not the only ones. The core thing that I think you need to grasp before talking about this is that nodes have IP addresses that exist on a real network. Let's say the network where they are physically plugged in, and the IP space of this network is often entirely different, in most cases will be entirely different than the IP space of the cluster. So clearly you cannot just take a packet that says, go to the pod, I want to send an IP packet to, for example, 10.185.1.1.1.6, and you cannot just drop it into the network and expect it to work. That will most likely not happen. The router that is governing the network where the nodes are physically plugged in knows nothing about these weird addresses. So we need to do something, right, for this to work. And there are, again, a couple of ways. One of these is through tunnels or different types of encapsulation. A popular one is, for example, VXLAN. And this will be used either by default by many CNIs, because this almost always works, so it's a reasonable default. And it's also very useful when the nodes, and even mandatory, when the nodes are not sharing a physical network. That means that both nodes, or in this case two, but whatever number of nodes, are not connected to a switch, let's say. In network, in more specific jargon, we will say they don't belong to the same layer 2 network. They only communicate through IP. Means they have a router in the middle. And we want to do some kind of encapsulations, because again, this router, which we need to go through, because we are not in the same layer 2 network, like topologic, then this router does not know about our cluster network. It has no idea about this IP address. So we need to do something, because we need to go through it. So encapsulation is one way to kind of work around this. So what the nodes will do, instructed by the CNI will program the appropriate subsystems inside the node for this to happen. It will tell, whenever you need to go to this pod, you're going to send a packet to the node's IP address, and the payload of this packet is not going to be the actual IP payload. You will actually encapsulate this into another protocol, and inside the payload of the protocol you say, this packet doesn't really go to you, it goes to somewhere else. It goes to this pod inside the node. This is called encapsulation or tunneling, basically putting a packet inside another packet. There are many ways of doing this, but this is one of them. And again, we need to do this because we don't, because the router that allows our two nodes to communicate doesn't know anything about the pods. Now this doesn't, this thing I have repeated a couple of times, that the router doesn't know. This is not enforced and this is not mandatory. You can make your routers aware of the networking shenanigans that are happening inside Kubernetes. There are quite some CNIs support such advanced use cases. Most of the time they will use BGP to communicate these routes to the router. Other times they will rely on SDN, so routers that are SDN enabled and can communicate with the cluster. But for the majority of the cases, this will hold. The network will be independent of the cluster. Question?
Yeah, I have a question.
Yes.
For example, if I use BGP to create like a mesh
Mm-hmm.
among all the nodes, then I can avoid the encapsulation to reduce the overhead of the communication between the nodes, or no?
Yes, that's correct.
It's possible?
Yes. Should I repeat the question? Is this again, is the microphone?
Yeah, if you repeat the question.
Yes, perfect. So the question was, if you use BGP or other protocol and communicate with the router and inform the router of all these, kind of routes, actually, of which pod is where, can you avoid the overhead of encapsulation? And the answer is yes. And it's, in fact, a common way. If you have very network-heavy clusters, you will want to do this. That is, if you cannot afford to put them in the same layer 2 network, which is way easier, and it's the part on the right, which I've called direct routing for the lack of a better word. But it works like this, and it also avoids encapsulation, which is sometimes a hefty performance benefit. So let's say that we have our 2 nodes, same as before, but this time we put them in the same LAN, in the same network, in the same layer 2 broadcast domain, if you will. So in this case, you can see that both nodes have IP addresses that look like they are on the same subnet. So one is 1031 and the other is 1032. So if our CNI is smart enough and supports this use case, we can actually tell the nodes, hey, when you want to communicate with this subset of pods, do not encapsulate the traffic, because the node where these pods are is actually reachable through the link you are connected. So we can go there, and if you can see the snippet, the code snippet on the bottom right part, and if we go into this, for example, the first node, 1031, and we do IP route, this one is cropped for clarity. You can see that the node has a default route, okay. The node has another route, which is like the classic local network route, and there is a third one that is saying this space, this /24, send it through this address, through this gateway, so-called. So this 1032 gateway is actually the IP address of the other node. So here, what the CNI is doing is abusing the fact that both nodes belong to the same physical network, and is going to send packets directed to these addresses, these 10, 185, 30, whatever. They will, the node will be configured to encapsulate the packets directed to these addresses into an Ethernet frame with the MAC address of the other node, and then we won't need to encapsulate anything, right? Because that's how IP networks work. The other node will, of course, have, you can see the matching route for the things to come back, kinda needed. If you have ever done weird shenanigans with networks, you have probably experienced how frustrating it is that you forget or you misconfigure the return path and your packets go out, but they don't get back. The response don't get back, so we kinda need that. And in this case, in the diagram, there is no router because the router is completely oblivious that this is even happening. The switch, the layer 2 equipment is saying this, but yeah, it's fine. This is just normal traffic. It's host doing host things. Our router is not even aware of this. This is very fast because this you forfeit all need for encapsulation. But it has this requirement that both nodes need to be they need to see each other in the same layer 2 network. Depending on where you run, this may or may not be possible. I will say that it depends. If you are running, for example, on different availability zones, on different cloud networks, this will probably not be the case, depending on your provider. But you can make this happen. Nowadays, network engineers tunnel layer 2 through big fiber trunks, and nobody really died. So it's a real possibility. Okay, so we talk about pods, and we talk about pods having IPs. And I vaguely told that the CNI is most of the time responsible from giving the pods these IPs, but how actually? how does this actually happen? Again, this may depend. You may have sophisticated CNIs with sophisticated use cases, but the baseline case, for the vast majority of things, it works like this. This is called, by the way, IP address management, or IPAM. You will see this acronym at least another time in the deck. Try to remember it. And it's again, for simple cases, it's a team effort between the CNI and actually the control plane. So on the left, you can see a snippet of the kube controller manager. The controller manager is part of the control plane. It's actually the biggest brain of Kubernetes. It's doing all the things. And this is actually configured. I have cropped a lot of things and left 3 specific arguments that I think are relevant for this. So these 3 arguments that you can see, allocate node siders, cluster sider, and service cluster IP range, these are configuration values that you either are the defaults or you configure when you create the cluster. And this is telling the controller manager, hey, this is the chunk of addresses that you will use for services, which is on the 3rd argument. And before that, you have the cluster side. And you can see it's 10, 105, 00, 16. And that is the base address range that the controller manager reserves for pods. And it looks like, well, it is as last 16. It is not just 65k addresses randomly allocated. There is a certain logic to it. And you can see on the right that there is the spec of a node. This is what you get if you run kubectl get node YAML. And again, I have highlighted here in the spec this pod sider. And pod siders is often a singular and a plural thing for Kubernetes reasons. And you can see that this node specifically is using 10, 105, 6, 0, 24. So what the controller manager is doing is each time you create or register a new node, it will take your cluster sider, it will slash a portion of it, in this case is a slash 24 out of this sider, and will reserve that sider for this node in particular. And if you think about it, there is at first glance no big reason why this should be done like this. Like, we do not really care, we do not really have a strong need to dedicate fixed portions of the cluster sider to its node. But if we reserve a specific subnet for each node, then that allows us to do what we saw on the slide before, right? If each node has a well-known and well-defined cluster range, then we can create routes on other nodes that are saying, this whole sider, this whole slash 24 is on this specific node because I told it was going to be. So this is one of the many examples of things that do not need to be like this, but if you do it, you get some things in return. So yeah, this is how pods get IPs. Questions about pods before we dive into services? Otherwise, you can just interrupt if you're not. Cool, then let's talk services. So I've been rambling for quite a while about pods, pod that and whatnot. But it turns out that pods are not that important in the grand scheme of things, at least not that important when applications talk to one another, right? One application that is of course running on a pod, but that's not very important, when this application wants to reach another application, it will, for the vast majority of cases, it will not target another pod directly. And the reasons for this, some we already discussed earlier when I was saying that the pod addresses come and go, and that it's kind of tricky to rely on DNS for this. So, and those are like functional reasons, but in terms of feature-wise reasons, if we make applications talk to services instead, then we benefit from load balancing, because services, what they're providing is layer 3 load balancing for your application. So you will typically have here, if we hop into it right for a moment, we have a service called MyApp, which has an IP address, that happens to be that. And that service called MyApp is grouping 4 pods in this case, which may be on different nodes, it doesn't matter. And what a client will do is connect to this service in particular. So the client will go there and say, hey, I want to talk to 10.96.142.37, and the client will be none the wiser about where this ends up going. For the point of view of the client, it is talking to 10.96.142.37. So in addition to load balancing, what this gives us is address stability. Again, I hinted this a couple of times, pods can go, and it's kind of tricky to keep, to assume the replications are prepared to handle this, but the IP addresses for services are actually quite stable. As long as you don't delete the service and then create it again, then the IP for the service won't change. And this is something the applications love, because then they can resolve once and then not think about the answer again in the example. The services also provide DNS. That's actually several buzzwords. Let's say that Kubernetes provides DNS for services. We will talk about that in a couple of slides. Regarding services, there are actually quite a lot of types. I mentioned 4 here, and actually I'm not sure if those are, maybe I'm missing one, but I think those are the most important ones. And in fact, no port, we won't talk about it every month because it's like very annoying. So we have different types of services, and these are actually kind of a superset of one another. We'll talk about that. I keep hinting things. You can see this is going to be a lot of fun. The most basic service is the cluster IP service, the one that has type, cluster IP. I think I should have, yes, for example. You can see type, cluster IP. Don't read further. Don't get too far away. The cluster IP services are the most basic ones and are just basically this. It's a stable address to which you can resolve via DNS, and that is going to load balance all the pods that are selected. We also have load balancer services. These are going to be conventionally understood by pieces of software called load balancers to be made available from outside the cluster. We will see an example of this. And you also have node ports and external name type services. Node port services select ports on physical nodes. These are not very much used in production because you need to tie them to, you need to reserve the same port on every node, and that is very much not great. And external name services are a bit weird. They allow you to forward traffic somewhere else. They are interesting for use cases, but not very important. Now, when you may have seen, you may have noticed that when we were talking about how pods have IPs and belong to nodes, but that the traffic, the communication between pods is handled by the kernel. This is actually somewhat similar. The communication, the actual load balancing is not done by Kubernetes, because Kubernetes loves not doing things and loves delegating stuff to other people who write that software, right? So there are, when either as a part of the default golden Kubernetes distribution, you will have a piece of software called kubeproxy. Daemon set actually runs on every node. Or you may have other stuff, for example, Thelium can replace kubeproxy and do this for you, but you will have something that is taking care of the load balancing. And the way this will work, against a bit of a spoiler, is also through Linux primitives. So again, Kubernetes is avoiding doing any kind of work and delegating stuff away. Before we jump into that, let's talk very briefly about service icon, which you already know, means IP address management. For most of the services, well, all services have a cluster IP, even if they are of another type. That's why I hinted that they are supersets of one another. And this cluster IP in the YAML on the right, you can see, for example, this 10.96.142.37. Where does this cluster IP come from? This is the subject of IPAM. And for the majority of the cases, this time the CNI will not be involved, and the controller manager will pick it directly. So if you remember a couple of slides before, we were telling the controller manager to an argument, this is the namespace that you can use for services, and it will just pick it at random. Or almost random. there is a tiny thing that the controller manager does for us, which is interesting for some things. We'll see it later. This is starting to be the catchphrase of the presentation. That is, you see this weird formula here, the main max CIDR size and whatnot. This, if you do this math in your head, congratulations, you're pretty smart. What this means is that there will be a segment of this CIDR, of the CIDR for cluster IPs, CIDR subnetwork is more or less the same thing, that the controller manager will try to not allocate. So if it runs out of any other IP addresses, it will start allocating this, but by default it will try its best to not to. And this, the size of this segment is at least 16, regardless of how wide or how big the CIDR is, and it is at most 2056. So at most it will be a slash 24. And this is, again, I call it a static-ish segment, is a portion of the service address range that the cluster, that the controller manager will not allocate unless it really, really needs to. And what this allows us is to actually pre-allocate addresses for some services in this segment. And this is needed or can be useful in some cases. For example, if you really don't want to use DNS and you want this particular service to have an IP address that is known and static and global for the cluster, then you should definitely pick one of those from first 16 to first 2056 addresses, because these are the ones that are guaranteed that the controller manager will not take from you. Again, and it's really, really necessary. That's icon for cluster IPs, the services for load balancer services, your load balancer clusters. End of the. Cool. So, load balancing. Let's see how that works. I will not go through all the commands, but let's see a simple example. Let's say we have a service here called my application, my app, which has this IP address, 1096. And this service is targeting 3 ports. So what any application will expect is that when it tries to connect to the service IP, it will go to one of these other pod IPs. So again, Kubernetes is not doing this, kubeproxy is doing this. And actually the name kubeproxy is a bit misleading because, you know, it is named like proxy. It kind of makes you believe that it's proxy and stuff. It isn't, that's a lie. Like many names in Kubernetes, that's a lie. What kubeproxy is doing is creating IP tables, not filter rules, that will make the kernel do this for you. So if you glance not much in depth, and I don't have that much time, into the output of this IP table save command, you will notice a couple things. Let's see if we can pick just a few. For example, the first one should be 142 here. I'm not very good, so let's see. This line, the one that ends here, that is saying, is this the one? No, that's not the one. Where is the 47, 147? I missed it. 142.37, yes, this one. So what this one is saying is, whenever you see traffic coming into this address, this is the address of the service, move it to this chain, which has a randomly generated name, kubectl Java. You can see that this chain is actually referenced below. And it says, for this chain, for every packet that arrives, with a probability of 1/3, send it here. And here being here. And you can see that this is the IP address of one of those pods. If this probability is not met, then we will fall back and we will fall back. IP table is a bit weird, but if you do the math, you will see that these 3 lines, when evaluated in sequence, have exactly 33% chance of getting either one of those. So then there is a bunch of other rules that are ensuring that, you know, traffic is mapped properly, masquerading is done, all this networking boring stuff. But the point I want to convey here is that Kubernetes is doing nothing and kubeproxy is doing nothing. It's just telling the kernel, do this for me. And this is how load balancing works. Question?
Yeah, I have this already.
No, go ahead.
For example, if I have like if I have heterogeneous nodes, can I keep some privilege to do the load balancing to a specific node.
Yes.
Node. Can I manage this?
Yes, to a certain extent. So the question was, if my cluster is not heterogeneous, can I somehow prefer, do some kind of hint the load balancer to prefer some endpoints instead of others? I can imagine that, for example, you are thinking when you are running in different data centers and hopping data centers, for example, hopping availability zones, that you will call data centers in the cloud jargon. There are some latency and even cost benefits from doing that. And the answer is yes. I did not include it in this in the talk because the time I have is unfortunately limited, but there are a couple of ways you can do this. There is one traditional, many ways, but important, I would say there are two. There is a traditional limited way and a more sophisticated one. So in the traditional limited way, you can do this very easily for nodes. So you can flip one flag in one of the parameters on the service, and the service will become node local, and it will only target pods that are in that same node. That's something you can do. And the second way is called topology hints. Topology aware. You have two names. Does anybody remember? Topology hints. Help me out here. Topology.
For the endpoint slices, right? You can have endpoint slices that you can select.
Yes, that thing. How is that thing called?
Topology aware routing.
Topology aware routing. Thank you. So that is a relatively new thing, where if you met specific requirements, that is, you tag your nodes in a specific ways, and the controller manager sees, well, inside the controller manager, the endpoint/controller in particular sees that you have enough nodes inside of each zone, then it will distribute the endpoints of the service in a way, tag them appropriately, so then kubeproxy or your CNI can pick those tags and make that happen. So it's a bit convoluted, but it is possible. Thankfully, you don't really need to think too much about that. You just tag your nodes and it will happen automatically. You just need to enable the thing and it will happen automatically, but the way it is working is like that. Again, your implementation, in this case kubeproxy, will need to understand that. But, Kubernetes ecosystem is usually consistent. So yes, that happens, and it's definitely possible. Again, there are more ways. Before this thing existed and before endpoint slices existed, some CNIs allowed you to do this, let's say, outside of the Kubernetes. So there wasn't a Kubernetes API for doing this, but you could do some annotations in the services, and some CNIs will understand those annotations and make that happen anyway. So yeah, there has been a way to do this for quite a while. It just recently got standardized. Recently, I think it was 2020 something, so not that recently. But yeah. Cool. So cluster IP services are cool and all, but if we are running applications in Kubernetes, at some point we will want to make those applications reachable. It is kind of the point. The canonical way to do this is through load balancer services. These are the kind of services that are meant to expose your applications to the world. They are not that different. You will see. They also have cluster IPs. They just have some extra spices sprinkled on top. And the key to understand load balancing services is actually not the type load balancer. Type load balancer is just a label that they slap on them, and everybody more or less understands what it means. But what makes that possible is actually a field called external IP. So services, if you allow me to go back, you can see that there is the cluster IP in there. So in addition to that, I don't think I have YAML for that. No, I missed that. So in addition to that, they may also have an external IP. And any service of any type can have an external IP. Again, it's very loosely tied together. So that external IP, let's say, for example, that you have the same service as before, the same cluster IP, and it has the same pods behind it. we can slap into the service and tell the service, your external IP is now 1234, which is an IP that is external to the cluster, as the name implies. So if that happens, you can see again in the top right some IP table gibberish created by kubeproxy that includes this external IP. And I think it's actually the second command. Yes. So it is saying any traffic that arrives to this node or to this chain, but trust me, from the global chain it gets to this. Any traffic that arrives to this IP 1234, you can send it to kubectl. And below you can see the definition of kubectl on top. Actually, you can see the definition of kubectl, which just says go to kubectl. And kubectl is the same as before. It's just some IP tables command that is randomly distributing the load across pods. So you can see that to make this available externally, we didn't have to do much. We slapped a tiny field in the YAML of the service. Kubeproxy picked that and generated one tiny extra IP table rule, and that's it. Now this is kind of a bit of a lie, right? Because yes, traffic that arrives to this node directed to IP 1234 will work, but how do we make traffic directed to 1234 actually arrive to this node? One of the options is that maybe 1234 is the IP address of the node. Yes, this can happen, and this will work. You have a cluster, your node has a public IP address, you set that public IP address for any node, because this IP table commands these routes are another node. So you take the public address of any of your nodes, you slap it in your service, and this works. Nothing more to be done. This is not very great, right? Because if we have Kubernetes, we have our applications, it has multiple replicas, we want it to be highly available and whatnot. If we are relying on one single node to be up and ready to handle this incoming traffic before it is distributed further, then we are not really highly available, right? We are in some regard, but we do have a big ass point of failure in there, which is that particular one. So there are a couple of ways we can mitigate this. One of it is we make our router aware of the 1234 IP address, and then our router, we tell the router, yeah, you can, for anything that comes to 1234, you can direct it to any of these addresses which are node addresses. When we do that, we don't call the router a router, we call it a load balancer, but it's kind of, at this point, level 3 is a bit of the same thing, if network people forgive me for saying this. So that is one way. You can have a dedicated host that is your load balancer. If you are in the cloud, this will not be a dedicated host, it will be a dedicated something, but it will be this. There are another way we can do it, which is with MetalLB, for example. MetalLB is not the only piece of software that is allowing this. Some other does. For example, Cilium coincidentally allows you to do this, and there are, I think, at least one another that I'm forgetting the name, but MetalLB is the one I use, so we can see how it works. I think it's pretty neat. The most hardcore network enthusiasts will enjoy this. So we have established that cluster IPs to pods are basically settled. They are by kubeproxy. Kubeproxy redirects them by means of IP tables. It does the same for external IPs to pods, but again, as I said, if we use a node IP as an external IP, then we are not really much highly available, because we depend on that node answering packets direct to that IP. So a solution for that is virtual IPs. So we can have an IP address that is not fixed to any machine. It's just one IP address allocated however we please. And then we can have this tiny neat piece of software which is called MetalLB, which will make sure that this IP, that there is one machine answering to queries to that IP address. So if you look at the diagram on the right, it's a bit confusing. So if it is more bearable if we start from the middle, from the router. And let's say that to our network, to our router, to the edge of our network, arrives one packet directed to 1234. And again, none of our nodes is actually 1234. they have other addresses. So what the router will do is send an ARP broadcast saying, hey, who on this network, who of you has 1, 2, 3, 4? And there will be, on each of the nodes, there will be a tiny pod called MetaLB speaker that communicates together through gossip, and by using a very, I would say, very clever, consistent hashing algorithm, they will agree on which is the node that now has to answer is backing this virtual IP, which in this case will be node 1. So the speaker in node 1 will actually respond to that ARP request to the router and say, hey, I as the node, have this IP address. And the router will say, fantastically, then I'm going to send you all this crap. And the router will do the usual IP thing. It will encapsulate packets directed to 1, 2, 3, 4 to the node MAC address and send it through the highway of Ethernet. And I think this is a pretty clever way because it is using very standard network protocols such as IRP. So it makes virtual IPs very easy to integrate with networks that do not have any shenanigans, that they do not have BGP, that they are not SDN and whatnot. So it's pretty good. There is a consistent algorithm and the nodes are essentially taking turns. With this piggybacking on the external IPs, then we have made our application available. Okay, this was intense. Questions about services before I delve into DNS, which is our fan favorite. Cool. If there are any, again, please interrupt. So let's talk DNS. When I started talking about services, as you see, one of the many nice things about services is that they provide a stable IP address, and this IP address can be resolved through DNS. Now, how do we make this happen? Right? What DNS is doing this? The answer is kube-dns. kube-dns is a Kubernetes-aware name server that you will see will bridge the gap between the logical world of the Kubernetes API where services have endpoints and whatnot, and the traditional or standard world of DNS where you ask for a name and you get the stuff. kube-dns is implemented by core DNS, and you may see that these two are used kind of interchangeably, but you can use core DNS for things that are not Kubernetes. So I think that the most accurate way to refer to the core DNS that is deployed in your cluster and is answering these names is actually kube-dns. It can resolve services by name. It can also resolve pods. This does not happen by default, but if you tell Kubernetes, hey, this pod should be resolved through DNS, it will make it happen. And if you see on the right, this is the shell inside a pod. Doesn't matter which one. And I'm trying to resolve some name. Right? And that name you can see is otlp.mon.sbc.cluster.local, which is hard to come out with. This is actually a convention. This is defined, probably defined somewhere. I've never seen it formally specified. This is the way you do it. This means that the pod here wants to know the IP address for a service called OTLP, which is in a namespace called monit. And this sbc.cluster.local is kind of a shared domain that indicates, yes, this is a service inside the cluster. This is configurable, at least the cluster.local part, for most of the time it will be the case. So you have probably seen this, the sbc cluster.local. Since this is a lot to write, you can also do it in a shorter way. You can use otlp.monit, and that means the same. This is a service called otlp in one namespace. You can see I need to add a search there. That's a big scenario that doesn't obey search by default. If I were already in the monit namespace, just using OTP will work. That's also neat, and that's also why you sometimes see Kubernetes applications referring as, yes, my database hostname is Postgres. Well, Postgres will be a service inside that same namespace. How does this work? Well, if we go again in the same path and we got the etc resolve conf file, this is very old, is the place where Linux distributions traditionally store the DNS configuration, you can see there is a lot of stuff. First is the search, which has a lot of things. This is what makes the short clear as possible, and not entering into the details of DNS here, but DNS will basically try each of these things in order before trying to give up, in order to fully qualify the domain name. The one on the top with cluster local is called fully qualified, especially if I remember to add the dot at the end, and the one below. Most interestingly is the name server type, which you can see is 10.96.0.10. And that's kind of interesting, right? That's an IP address that is there. Why that? Where does that come from? Who created this? And the answer is, as usual, very interesting. Oh, TPI has messed it up. Pretend this code block is not intersecting with the footer. Doesn't look directly at bugs. So what is 10.96.0.10? It's a convention, like many things in Kubernetes. It's a convention, it doesn't mean particularly anything, but the kubelet knows about this convention. And if you look in the bottom right, so this part here, you can see that I am showing a snippet of the kubelet configuration. This is a file that is on every node and is what made the kubelet work. And the kubelet is being told directly by config, hey, the cluster DNS is this. There is no more magic to it. So it's somebody told the kubelet, the DNS that you should put on the etc resolve files of the pods is this one. Now, this address actually exists, thank God, otherwise we won't be able to resolve shit. And if we go to the, again, this is the resolve conf on the top middle, I will guess. We go to the bottom right, we can see that there is an actual service like this. It's called kube-dns, it has this IP address, and it is selecting pods that actually run core DNS inside the cluster. Now you may remember this top right part is kind of a flashback that I told, you know, there is this special portion of the cluster side that is static and that the control manager will allocate automatically. That is at least 16 and it is at most 256. Well, 10.96.0.10 is actually one of those addresses. So whatever we used to set up Kubernetes, maybe kube-dns, maybe, I don't know, our cloud providers did this, whatever we used, pick this address like out of a whim because it looked fancy, you know, it could be anything. It is 10 because somebody thought 10 was a round number, and say, you see this address here, the .10, is actually inside this static segment, so I'm going to use that, and this is what you get on the service, and this is how DNS works, or how pods are able to reach kube-dns in the cluster through this convention that someone said here, and we all understand and we are going to follow. I think this is quite neat. Like, it really, for me at least, it really demystified this a lot. Like, how did the DNS in Kubernetes? This is you know something very difficult. Well, it turns out somebody picked an IP address and put core DNS in there, and that's it. And the controller manager pinky promised to not put anything else on that IP address. Cool. So what is actually happening when we are, we are in the leftmost part, we are pod client, and we are trying to reach an application called my app. How does this work? Well, you probably kind of know already, but let's go over it just to be safe. So pod client will run a DNS query called what's the A record, most likely, for myapp.svc. To kube-dns, we know that pod client knows about kube-dns because it's hard-coded in its etc resolve code. Kube-dns will receive this and will forward kubeproxy, actually, this is a service. Kubeproxy will forward this to one of the core DNS pods that are on the cluster. Here is this one, MCJ85, just one. So core DNS will, in theory, this doesn't happen exactly like this, but bear with me for a moment, will go and ask the API server, what do you know about service my app? Can you tell me the things you know about service my app? And the API server will tell you, yes, service my app is a service, and these are the IP address, and this is the cluster IP for that service, which is 10.96.1.7.42. So then core DNS will forward that back to pod client, and pod client will know, okay, this is the IP address of the service for my app. So then it will try to connect to my app, the kubeproxy will do again its thing and will direct that to any of the pods back in my app. Again, this is for cluster IP. This is, we have already covered most of this, but I think it's kind of neat to see it all together. Now there is another type of service that I haven't talked about, but is particularly relevant for DNS, called headless services. And the name, as many Kubernetes names, is terribly bad because you see headless services and that I'm betting doesn't tell you anything unless you know about them already. The headless what? What is headless? So headless services are services that do not have a cluster IP. So they just exist there in the control plane, in the database. And they have, they are also backing pods. So there are pods actually behind the service, and these pods are registered as endpoints in the service. So the API server knows about the pods that are behind the service, but the service itself doesn't have an IP. So this allows us to fulfill some niche use cases where we do not want load balancing to happen. So we just want to use DNS as a discovery mechanism, but we do not want kubeproxy or anything else to perform load balancing for us. There are some niche cases where we want to do this. For example, some applications may want to implement their own load balancing. We will see more about this later. Or there might be other cases where, they want to contact all backing pods at once because, this is a database and they want to distribute queries in a particular way. There are some niche but specific and very, very different use cases when this may happen. What will happen here is that we can still use DNS for this, and again, the pod client will say, hey, give me the records for my app SVC, or go to the kube-dns, will be forward to call to the actually core DNS pod, which will talk to the API server, and the API server will tell, yes, this is the service, these are the endpoints, and this time, core DNS will return all of them. And we'll return to the pod client a DNS response saying a record for this service is this, and another a record for this service is this. And now the client will have full visibility of the two IP addresses that are in the diagram example. There are two. With these two IP addresses that are actually back in the service. And then pod client may implement whatever technique it wishes to contact both of them. The first one, the other. Again, this is for niche use cases. Most of the time you want an IP address. There are a lot of advantages of using a load balance IP address, but again, for weird things like databases or specific load balancer, this is very interesting. Cool. Questions about DNS? Yeah, let's move on. Yes, question.
By default, you can access different services from different namespaces.
Yes, that's correct.
What is the best practice way to limit that?
Okay, so the question was that if by default you can access services on whatever namespace they are, and if that's the case and we don't want that, how we can limit that. So yes, that's the case. Kubernetes by default, at this level, it doesn't impose any kind of restrictions. In fact, as you have seen on the kubeproxy examples and the ptl command, there is no notion of namespace in there. Kubeproxy knows nothing about that. The way you do that is through an object called network policy. So most CNIs, among many other things, will also understand what a network policy is. I don't have a slide for that, but I can tell you and Google that. It's basically a YAML that you put in the cluster, and you are registering in the API server of the cluster this particular set of pods on these ports can only be accessed by this other particular set of pods. Typically you use selectors and namespaces for this, so you select the namespace and you select a subset of the pods or all of them on this namespace, and you say only these other pods or namespaces can reach those. This, as it is the theme in this talk, this just sits there in the control plane, and the CNI will dutifully request periodically, okay, give me the network policies for the cluster. The API server will give the objects to the CNI, and the CNI will make that happen. in many different ways. It might do this through EPF by inserting some probes in there and doing the traffic. It may generate different IP tables rules. And whatnot. I'm actually not sure about how kubeproxy does this. I'm not sure if it generates reject rules or drop rules on top. Or I will suspect so. Don't quote me on this one. But the CNI will take care of that. And network policies are the way. Okay, so ingresses. All we have talked until this point has been level 3, so we have talked about IP addresses and DNS, but this is the century of the web. So to call it everything is HTTP on this day and age. So HTTP kind of gets favorable treatment in many ways. It's not just a protocol, it has like a big ecosystem around it, and since developers will almost surely care about HTTP, there is a specific set of APIs and objects that we can use to route HTTP traffic in Kubernetes. Ingresses is the most traditional way of doing this. There is another one called gateways, which I'm not covering here because I honestly know not a lot about it. So we can cover ingresses, which are I think pretty useful. So what ingresses do is layer 7 routing. So instead of routing by IP addresses, they perform routing by host. So by host name, in HTTP this is just called host, but we could call it host name, that is the google.com part of the URL, and also by path. So that's the /search part of the URL. They also perform load balancing at the L7 layer, and this is I wouldn't say misconception because it is kind of intuitive to think that ingresses use services. Well, they do not, or at least not directly. Ingress controls will talk to endpoints, we'll say that later. So they perform their own load balancing and can do load balancing in ways that are HTTP specific. For example, session pinning or directing, if you have a given cookie, you go always to the same path. These kind of things that would be impossible with Velocity. So ingress objects, once again, they're just a bunch of YAML that you host on the API server and Kubernetes does nothing with. And ingress controllers are the ones that are going to action all these objects. Some ingress controllers that you may have heard of are ingress nginx, which is, as the name implies, based on nginx, and also contour or graphic. I happen to like ingress nginx for topic operations, that's the one I'm familiar with. Yeah, in a way, it's the easiest. At least, yeah. Another thing ingress controllers will do is terminate TLS for you. This is pretty neat. You can see there is some TLS related stuff in there in the YAML on the right. That's because that's the reason for that. And there are many things that integrate with ingress objects. For example, external DNS, which I'm not talking because this is about today, because this is pretty long already, or third manager, which you can use to actually, to actually get those certificates. And on the right, no point going through it, but you can see more or less what an ingress object looks like, and you can see that there is a host and a path, and that is basically saying, okay, request to Nadia.mobile that go to the path / and anything after that, so that's every path, goes to the service called website on a port called HTTP. And you should also use TLS certificate, which is in the website third secret, so there's a secret named website third, then there's an HTTP certificate that you can use for these two points. And then you can see the status where the ingress controller actually populated the IP address of the load balancer inside here for reasons for integrating with other stuff. It's not really related to anything. So how does this work? Well, ingress controllers are also services, to no one's surprise, because they need to be reachable from the outside. We already more or less know how this works, so we can answer it. So we have the internet is making a request through us. This request will be an HTTP request, a series of network packets that form an HTTP request, and this is also TLS enabled. The request will go through a router and will go to any node. and this will happen because the English controller is inside a service with an external IP, maybe a load balancer service, maybe something else. But the node will take care of routing that to a pod, which in this case is the English controller. Yes, this is what you see here. The node goes to the English controller service, and the English controller service says, this English controller pod, this is the pod last there. The English controller box is a pod. This is the one that will take care of an request. So what will the English controller do? The English controller will ask the API server, hey, I have a request for Nadia.moe before this example, and I have an English object here that says that the request to Nadia.moe must go to the pods backend service, back in the website service. Can you tell me what are the endpoints of the website service? And the API server will beautifully return this and tell the English controller, yes, these are the two pods. And here, this is one of the examples I hinted before, where the services will not be accessed directly. You want to know the actual endpoints behind, because the English controller wants to implement this layer 7 routing we were talking about. The English controller wants to be able to pin sessions to cookies and to direct based on, I don't know, A/B testing or blue-green deployment, or basically whatever the English controller thinks is a good idea to do. So that's the reason why the English controller will not direct traffic to the service IP, but rather to one of the endpoints of the service that is chosen. And in this case, the request will end up in the pod website BH diagram. And the green lines mean that this is the traffic flowing still as encrypted. Typically, the English controller will terminate that, the English controller will have your certificate, and beyond that will proxy pass the traffic to whatever without HTTPS, without TLS. Most likely. Again, maybe it's my vary, but it's pretty convenient to not have your application care about TLS because it is a mess. Cool. So to recap, we have learned, hopefully, a lot of things today. We have learned what containers, pods, and services are. We have learned how pods communicate within the same node or across. We have learned that services are the primary means of reaching an application. They have stable addresses and stable names. We have learned how those names are resolved by kube-proxy and how, by kube-dns, but we have also learned that kube-proxy implements this forwarding for cluster IP and external IPs to IP tables. Again, the DNS thing, which I'm missing the bullet here. And we have also learned that metal-LB can be used to back load balancer services through IP addresses. And finally, we have a glimpse at how English controllers work. I hope this was interesting, so thank you for attending. Questions? We have covered a few during the talk, so there may or may not be.
Could you say a couple of words about IPv6? Does it really work in production? Because you see the documentation, it's kind of, yeah, okay, we have IPv6, but it still looks like second-class citizen.
Very interesting question. So the question is, what are my thoughts about IPv6 and whether I see it still as a second-class citizen on the internet? So, a couple of years ago, I was actually an IPv6 hater, and I am still a bit. So a couple of years ago, if you ask the couple of years ago Nadia, she will tell you IPv6 is a mess, because you effectively need to care about twice the stuff. You have a different firewall, you have a almost different network stack, you have different, obviously, addressing space, and that is basically doubling the work that you need to do to make your network work. And the current journey still stands by that, but I've come to also like it a bit. It does make some things a bit easier. I can tell you that I do run, my main cluster is IPv6 enabled, so you can reach, if you try to resolve Nadia.moe, it has a quad A or a record, so you can resolve it, and that will work inside the cluster as well. There are couple, so IPv6 in Kubernetes, just like outside, you can do two things. You can have your cluster be IPv6 only, so you will basically tell the controller manager, I don't know where I got example here. You can tell the controller manager the cluster side is a v6 sider and the cluster IP range is a v6 range, and it will work. Maybe you will need to tweak a couple of flags here, like, yes, this is really v6, I'm not crazy, like, make me casito, and that will work. Most of the, well, another way of doing it is having your cluster be dual stack. So that means that your pods and your services will have a v6 and a v4 address. So that can also happen. That is the case for my production cluster, the cluster serving my website, the Nadia website, among many other things, is actually dual stack because it started as before and it was easier to move to dual stack than it was to completely migrate. Some thoughts of it. I think the situation has improved. So when I moved my cluster to dual stack and I added v6 to it, it was not as painful as one might think. A couple of things broke, but they were like tiny things. I remember network policies breaking because I had a couple of places where I had, network policies allowing anything, and the easy way you have to allow anything in network lingo is say 0.0.0.0/0. That means anything. Well, no, it means anything before. It doesn't mean anything before MV6. So there were a couple of those things that you don't really realize that are before specific, that they need to iron out. But most of the time, anything else really just worked. No, I will add another thing. For load balancer services in particular, you have to also set in the service that this service can do both addresses, that this service is specifically dual stack. This is called by IP family policy. This is done by a field called IP family policy in memory reserves. And this is actually used by load balancers to know whether they should assign v6 addresses to services. This is not a problem for Kubernetes. You can do this all fine, but it is a problem for Helm charts. If you are using Helm charts and you know the pleasure that is to find that a particular Helm chart doesn't particularly allow you to modify one field that you wanted to modify, well, this is one field that nobody thinks you will have to modify. So every single Helm chart I have seen, except the English and Nginx one, for kind of obvious reasons, anyone else that I'm using to deploy a load balancer service, I have to make a PR upstream saying, please allow me to change the IP family policy field, because, I kind of need it. So you can still see that it's kind of a second-class citizen in the sense that not 100% of the people is aware of IPv6, but across the building blocks of the ecosystem is there. And I will say it's quite interesting. One last comment, I saw recently that there was one one person on the internet I didn't know about that actually dared to make their Kubernetes cluster v6 and give each of their pods public routable IPv6 addresses. And that was like, wow, okay, makes sense that you can do this. This is insane, but it's kind of cool that you can do this.
No, it's kind of cool because
it's kind of cool.
You don't need anything.
You don't need anything else.
Everything is IPv6,
yes.
And everything is just simple IPv6 routing.
Yes.
Kind of cool.
I can imagine that configuring your CNI for that is going to be fun. but it's also configuring your firewall. That's also fun.
For Nadia, for example, if you're running Digi and you have your servers in your home, and you have IP6, I have IP6 with microdig.
Oh.
Each device in the network, in the layer 2, in the layer 3, have a fucking IP public. Because Digi gives you, hey, here's the namespace. Everything behind this massive number, because it's 64 bytes, is public. And it's yours. It's a problem to manage. You know how many, and that is a vector of attack. because
Yeah.
you don't can put a fucking firewall.
So
It's a
there
mess.
should be a firewall in your router.
Yeah, there is a firewall in the router, but it's public address.
I have a
It's
bunch
crazy.
I have a bunch of friends that put NAT on IPv6.
Yeah,
They
yeah.
say, that's for security, but
No,
NAT
but
is not for security.
it's not for security, it's because it's laziness.
That's
It's
lazy.
easy. It's easier to manage a NAT than manage IPv6. Sorry, but it's true. Nadia is also telling that.
Yes, I have a public IP on DG.
And it's not, they don't give you a IP
No.
public, they give you a space. Hey, here's the space. Everything behind is yours.
Yes.
And they change you, and you need to reset the fucking router every time they change you.
Yeah, the change.
In microtik, you need to reset.
The fact is they change it is
I'm
easily.
using OpenWR.
Yeah, I'm using a microtik router.
I do have DG at home, but I haven't moved the piece.
No, I disable IPv6, giving me too much problems.
I did that. That was it.
Yeah, they give me problems of connect me to internet, so I disable.
Ooh, interesting. I have found the opposite actually. This thing I told you that 2 years ago it changed my mind and became I embraced at least partially IPv6 was actually because the peering I had with one of the servers I have on Germany was shit. Like shit, like 30 megabits per second shit. And we were like, I'm too tired of this, and this is a conversation I do not have to with my hosting provider because it will be very long, and with my internet service provider it will be even longer. So I don't want to have this conversation, but turns out that the basic experience is pretty good. So actually, instead of talking to a person, I could deploy IPv6 on my Kubernetes cluster, and that's how I ended up here. Yeah, but the tunnel runs over before, so yeah. So yeah, IPv6 is getting there.
Is it good?
And the building blocks are there. I think there will be another 10 years because before we can use it to connect to GitHub, but many other places actually implement it and it works pretty well. And you can do cool things. For example, my IPv6 kind of.
Was it dangerous?
Yeah, it was in the English, for example, kind of spells this Nadia part. I thought it was funny, and the cat phrase was also pretty funny. The column 3 at the end.
Nadia, yeah.
Yes. So yeah, I don't know. There is funny things you can do. I don't know. I can ramble about IPv6 or something more, but let's hope to something else. More questions? Going once, going twice. No more questions. Thank you very much.